Well, thank you very much, everyone. I have three different presentations that I will talk to today. They're all related to projects that we're currently doing through PTAC, but there is some linkage or relationship between some of the work we're doing in these projects and some of the work we've been doing under the NAMA initiative, or this Fast Start funding. This leading to the development of NAMAs in Colombia and Mexico. So where it's applicable, I'll try and make a few comments in that regard as well. The first presentation is on a study we're doing to better understand emissions from heated heavy oil storage tanks. There was kind of two objectives in this project. One was to understand the variability in these emissions and their relationship to activity levels in these tanks, but as well to understand the composition of the emissions that are coming off these tanks. So the basic objectives that are defined in the terms of reference for the project were to evaluate vapor losses, determine the variability in the emission rate, evaluate the impact of operating temperature on emissions, and determine the fate of and composition of any aerosol emissions from the tanks, and perform limited tracer tests to help delineate the behavior of the emission plume coming off these tanks, so we would be able to compare what we were measuring to what dispersion models would predict. The project is still a work in progress. The work that's been done to date includes the following. We've conducted measurements on 6 different tanks at 6 different heavy oil facilities in Alberta, 3 in the Peace River area and 3 in the Cold Lake area. These were all cold production facilities. There was no enhanced recovery fields that we were sampling or testing in. We conducted detailed laboratory analyses of the vapors coming off the tanks, as well as the casing gas that was occurring at each of these sites. And this work also included measurement of particulate emissions, both upwind and downwind of the tanks that were being monitored. The analyses that were done on the samples that were collected of the emitted tank vapors and of the casing gas at these sites included analyses using 4 different instrumentation methods. We used GCs with thermal conductivity detectors to quantify O2, nitrogen, carbon dioxide, and concentrations in these streams. The detection limits were in the range of 50 to 100 parts per million. We used an FID for C1 to C4 compounds with detection capabilities in the 50 part per billion range, and a GCMS for C5 to C12 compounds, and we had detection capabilities there in the range of 10 micrograms per cubic meter. And we also looked for reduced sulfur compounds, and that was done using a sulfur chemiluminescence detector with detection capabilities in the range of 1 part per billion. And these analyses were actually all done off-site by Alberta Innovates at their Trace Organics lab in Bakerville. So we collected the samples and shipped them to them. In addition, I should mention with respect to that, the analyses that were done use fairly comprehensive calibration standards for a number of toxic compounds of particular interest and photoreactive compounds. So the methods that were applied were consistent with TO15, TO17, and EPA's PAMS test methods. The collected aerosols were analyzed for both semi-volatile organic compounds, including polycyclic aromatic hydrocarbons and alkyl PAHs. In addition, we were able to do some measurements on a tank, not only during normal production type activities, but also during a desanding event. So on a typical production tank, they tend to accumulate sand in the bottom of these tanks and periodically have to remove that. There's an automated process, or I'll describe it later on in the presentation here, but there's a lot of equipment that's brought on, and the use of hydraulic systems and high pressure water jets to fluidize the sand in the bottom of the tank so that it can be drawn off the tanks. And when this is occurring, there's a lot of agitation of the product in the tank, and there was concerns that there might be, if not increased emissions during these events, as well potentially unique emissions during those events. So we were able to monitor one of these events And at the sites we went to, out of the 6, there was 2 sites that were actually venting the casing gas. So we were measuring the amount of venting that was occurring at these sites and have that information as well. So the outstanding work that we still have to do on this project is to, we'd like to do additional measurements on the descending events. The measurements that we did do, we had to change some of our instruments partway through the event to capture the full range of conditions that we were incurring. So the data set that we have is not as complete as we'd like to be for that particular type of event, so we'd like to do another one. We have an obligation to do 3 tracer tests as part of this work, so we want to as well find a tank where we can model the characteristics of the plume dispersion as the plume migrates away from the storage tank. And we also want to determine the impact of temperature changes on the amount of emissions that we see coming off the tanks, as well as on the composition of those emissions. And then of course we have the data processing and reporting to do that goes along with all of that work. The measurement strategy that we applied, we've tried to be as rigorous and as thorough as we could. And we've used a lot of techniques that are perhaps new to this type of application. In terms of the specific parameters that we were tracking, we looked at the liquid level, or sorry, the liquid flow rate going into the tank. We measured this using clamp-on ultrasonic flow meters. We used 2 types of flow meters, both a Doppler meter, which is better suited to liquid streams that have air bubbles entrained in them, or gas bubbles entrained in them, or solids, and then transit time ultrasonic flow meters, which are better suited to clean fluids. So as a normal course of what we do, tend to put both on there, so if we get periods where you've got fairly clean fluids going through, then the ultrasonic, or the transit time system will pick the flows up, and if you've got a dirty fluid going through, then the Doppler meter tends to pick it up. But the power of these is that they're clamp-on devices. We can go to a site and don't have to cut into the pipe or make any process changes or any shutdowns to be able to start measuring these flows. The liquid level in the tank, we also monitored that. We did that using a microwave radar system. So we were able to get continuous readings of the liquid level in the tank, and these are fairly accurate or highly accurate systems for measuring the liquid level in the tank. A lot of the sites we went to, we didn't see a lot of liquid level change, so simply referring to the normal board type gauges that are on these tanks was not accurate enough for the type of work we were trying to do. We put a vent gas flow meter on the top of the tank to continuously measure what was coming off the tank. We chose to use a transit time ultrasonic flow meter for that purpose. When we did this, in order to do measurements on a low pressure gas stream, the only way you can do it with an ultrasonic flow meter is to actually wet the transducers to the flow. So we did this by creating a flow cell. We had a flow straightener upstream of that cell to provide a good velocity profile through the cell and provide better accuracy when we were doing our measurements. And as well, the interesting thing with an ultrasonic flow meter is that you, in addition to measuring the flow velocity in the pipe, you also are able to determine the speed of sound in the pipe, and you can relate that to the molecular weight of the gas that you're seeing, and use that as a way of inferring the stability of the composition that you're seeing going through that particular flow meter. In addition to this, we had a series of micro gas chromatographs at the site that we were using to continuously monitor the composition of the gas coming out of the vent system, so that we could see if there was going to be any compositional variations with time and as a function of the types of activities that were going on in the tank. Casing gas flow measurements, we did that using a transit time ultrasonic flow meter similar to the one that was used on the top of the storage tank. And then we had a meteorological station at the site to measure wind speed, wind direction, relative humidity, and barometric pressure and ambient temperature, so that we could as well take the emissions that we were seeing and do dispersion modeling if desired to predict where the plumes would be traveling relative to the tanks and relative to where we were doing some of our monitoring. And of course we had the aerosol monitoring system, so we had a high volume sampling system that sampled both filterable particulate matter, as well as it had a polyurethane foam adsorption trap in it to capture condensable and a certain amount of non-condensable PAHs and heavier semi-volatile organic compounds that would be coming through. We also had 2 optical particulate matter systems that were set to measure PM 2.5, and again we had one of these upwind and downwind of the system. So overall we were trying to be as rigorous as we could and measure as many parameters as we could that would relate to what was happening in these particular tanks. The equipment that we were using to do this was all tied into a wireless communication system that was rated for a Class 1 Div 2 environment. So each sensor would draw power from well, we had these radio transmitters that had batteries built into them as well as onboard memory capacity. So we would tie our sensors into these radio transmitters, and that would power the units. It would collect the data from them at a polling rate of once per second, and it would send that information back to a base station. And then the base station would receive this information, and we could graph that in real time and observe the actual trends in the data as everything was occurring at these sites, which gave us a better understanding of what was happening and allowed us to see if something wasn't quite working properly when we were doing our measurements. So this first slide shows a typical site that we would have been at. We would have, in the foreground here is one of the high volume particulate samplers, and this is on the upwind side of the facility, and then next to it is one of the optical PM 2.5 monitors. Of course, the wellhead, and in this particular case, the casing gas is being used to power a small generator set which runs the pump on the well. We have our, well, the GCs are all set up in the van, and we'll have our flow meters down towards the tank here, and then we also have our meter up on top of the tank. And you can't really see it here, but the other particulate monitoring system would have been put on the top of the berm. And in the Peace River area, at least, there was a reasonable amount of reduced sulfur compounds in the emissions, so there was a perceptible odor from the tanks. We could tell when we had our PM monitoring systems set up on the berms there that we were in fact in the plume of the emissions coming off the tank, so that made it much easier there. In the Cold Lake area, it was much more difficult actually to smell the emissions coming off the tank, so we had to, for the most part, use our judgment in terms of where we were positioning. But basically we did the same thing at each site. We would position the monitoring units on the berm because that, in theory, is where residents and non-operator personnel would first come in contact with these emissions. This is just a photograph showing one of the meteorological station that we were using, and as well another PM monitoring station. And it just gives you an idea that in some of these locations there was receptors fairly close by. So here there's a residence just actually downwind of the facility. And there was also a highway that ran past in front of that building that had a fair bit of traffic that was going by. This is a photograph showing the clamp-on transit time and Doppler ultrasonic flow meters. So here we've stripped back the insulation on the flow line going from the wellhead to the storage tank, and the flow meters are the two devices you actually see here, or at least that's it provides local readout for those devices. They're both tied into this device, which is our radio transmitter, and can't see the antenna on it here, but there's an antenna that is related to this, and this of course sends the signals back to our base station. And then the transducers themselves are on the piping here. We also had clamp-on temperature sensors to monitor at least the outside temperature of the piping and relate that to the temperature inside the pipe. This is a photograph showing the radar system that we use to measure the liquid level in the tanks. So again, it's powered by connecting to one of our radio transmitters. It's got a special nozzle on it that helps to focus the beam that comes off that to avoid interference with the side of the tank. And here what we've done is we've simply threaded it into a 2-inch MPT connection on a steel plate that we just set on top of the thief hatch in the tank. This photograph shows our flow cell. So here we've connected to the vent on the tank, conducting the gas. There's a flow straightener right at the beginning of this flow cell, which you can't see. And then the gas, of course, goes through there. And then at this end, we are actually drawing out some of the vented gas, and it goes into a heated sample line and down to the GCs in the vans. This is the base station that receives the signals from the different radio transmitters that we had at the site, and brings them in and feeds it into a laptop computer where we can have real-time trend analysis of the different parameters that are coming through. And then this shows the micro GCs, gives you an idea of just how big they are. We've got one here from Agilent Technologies, and then we've got three, or actually in this case I think there's 4 in here from a company called Falcon Analytical in the US. And we're continuously drawing sample off the tank using a pumping system, and gas flow goes over top of a silicon canister. At one point during the sampling program, we actually take some of that sample and draw it into this canister, and then that would go off to Alberta Innovates for analysis. But the rest of the time, the sample is going through this array of micro GCs. Just another close-up view of what those GCs look like and how big they are. And this slide shows you a sample of some of the chromatograms that were coming off the unit. So this is the kind of information that we would see in real time in the field. And this is a more detailed diagram that shows a mix of the different data that we were measuring at the site. So the black line up here is the vent gas flow rate that we were seeing from the tank. So you can see it was going through periods where it was fairly stable, and then periods where it was fairly erratic. The blue line at the top is the actual liquid flow rate going into the tank. And the interesting thing here is that the liquid flow rate is not a stable, continuous flow, even though the pump is operating at a constant speed. The liquid that comes out of the formation comes out in a non-uniform flow rate. And you don't see this on a normal tank here because you never see the liquid actually leaving the end of the pipe. But we've done quite a bit of work in China where the liquids from the oil wells has gone into open tanks that we could see it coming out. And it was the same thing there. We see a very erratic, sluggish type flow behavior where you get the liquids coming through in surges. And the same thing happens with the gas that comes out of the formation. We see the gas coming through often sometimes in a stable formation, but depending on the well, sometimes it can come through in a fairly erratic manner as well. Down below is the composition results from the micro GCs that's expressed on an air-free basis. The interesting part here was that the composition remained fairly constant throughout. So it didn't matter whether we were having a filling event or an emptying event. It didn't matter if there was a burst of gas that had just come through. The composition, except for the odd little spike and a bit of noise in it, seemed to be fairly consistent. The unique feature between these two sets of graphs, which are for two different sites, is the first most abundant compound showing up in the vapors was methane, which, based on this graph, is over 90% of the vapors that are coming off the tanks. But on this graph over here, the next most abundant compound coming off is actually C6. And in this particular case, they were taking heated oil from the tank and then recirculating it back down into the well bore to help fluidize and bring up some of the sand that was tending to accumulate in the well bore. So it was a unique operation that was occurring at that particular site. But at the other sites, that wasn't occurring. So the liquids that were coming out of the well were much colder. And in those cases, ethane was the second most abundant compound coming out. But it does show that there is certainly some impact of temperature on these. I haven't had a chance to actually go through the detailed analyses, but things that were happening at these sites that would be of potential interest are the fact that most of the sites were injecting an anti-foaming agent, and that was going into the product that was going into the tanks. And so there's a potential for that to contribute to some interesting artifacts coming off the vents, but at this point we haven't had a chance to actually go through that data. The last thing here is the desanding events that were going on. It's actually quite interesting to watch if you haven't seen one, and for anyone that's not familiar with how this is done, I'll just briefly describe it. So what they have is a high-pressure water lance that's pushed into the tank through an open valve in the bottom of the tank, and it's done using a hydraulic ram, and the cords you see here are actually what powers this hydraulic device that pushes that pipe in and out of or that lance in and out of the tank. The pressurized water that's being fed through that is fed through this hose that's at the end of the lance, and this piping here goes to a vacuum truck, and what it does is it sucks out the fluidized mixture of water and sand that's at the bottom of the tank after it's been fluidized using this high pressure water lines. And the pressure lines from this go over to a pressure truck, so there's actually 2 vehicles on site when this is being done. And they would potentially go through several cycles where they would fluidize the material in the bottom of the tank, draw it out with the vacuum truck, let it settle in the vacuum truck, decant the water off, push it over to the pressure truck, and then do another iteration on the tank. In this particular case, they only needed to do 1 iteration to get all the sand out. But what happens during this is you see a lot of agitation on if you look at the board gauge on the tank, you see the float on that bouncing around quite a bit. And there's large volumes of liquid that are drawn out of the tank and then pushed back into the tank and drawn out of the tank. And all of this has the potential to contribute to the emissions that we're seeing. So what we found when we were doing the measurements here is that we were able to accurately measure the flows coming off the top of the tank and measure the change in liquid level. What did happen though was the devices we were using are set to a 4 to 20 milliamp output, and you have to pick what the limits of your operating range are, and we found that we had set the operating range too low for the volume of gas that was being displaced from the tank during the peak level of activity during these events. So we went up and changed that, and then it worked fine. So that's our thinking behind wanting to go back and do another one, is to get a complete data set for a normal desanding activity. This photograph shows us simply doing a casing gas measurement where we're measuring the flow rate of gas being vented to the atmosphere, and the same basic equipment, our flow cell with a flow straightener at the front end of it, our ultrasonic, our local readout for the ultrasonic sensors that are being used, and then the radio system that transmits the results from that back to a base station, which ties it into a laptop so we can see the graphs in real time. So a lot of the same equipment we're actually using in some of the NAMA work we're doing, and I guess the power of it is we can go into facilities, and it allows us to easily do a mass balance and an energy balance on a system without having to shut the process down and without having to tie into piping to be able to do these types of measurements. So it's been a big help in some of the work we're doing at refineries and production facilities and processing facilities in Mexico and Colombia.